Okay. So today we are going to look at topics from week 3. Okay. Fine. So today's topic, we are going to introduce a new topic which is called vector spaces. Okay. So what are vector spaces? Before even going to what are vector spaces, we will start with some sets which are already known to us, some familiar sets which we already know. So we'll start with that. We will see what are all the properties already are there for these set. Okay, we will have a first observation of such things, and then we will slowly see how these properties together form something called a vector space. Okay, then we will see what are the specific properties, some certain properties of vector spaces, and what are subspaces and other properties of the components of vector spaces, right? Okay. Fine. So first we will begin with what is called the system of linear equation. This is what you have been studying in the first 2 weeks, right? You have been studying what is a system of linear equation, how to solve the system of linear equation, right? So not all different ways, but some uh, aspects of solving system of linear equation is covered in week 1 and week 2, right? So we are starting with a system of linear equation, Ax is equal to B, where A is an m by n matrix. Okay. So we have seen a few ways of identifying solutions of this system. Okay. Now consider this set S is equal to set of all x in Rn such that Ax is equal to 0. What do we call this equation Ax is equal to 0?
Homogeneous.
Yes. This is a
Yeah.
homogeneous system, right? So now S is the set of all solutions of the homogeneous system. Ax is equal to 0, right? So now what do we know about S? What do we know about S? Is S empty or non-empty? What do you know?
Non-empty.
It's always non-empty, right? It's always non-empty, right? And it contains which vector? What vector is always there in this set? Yeah. So always, what is one solution of Ax is equal to 0? What is the obvious solution of Ax is equal to 0?
It's the zero solution, right?
Yes, yes. So it means the 0 vector always belongs to S, right? So it means here it contains the 0 vector. So 0 belongs to S for any A, right? That is why this S is always non-empty and it contains the 0 vector, right? So S is either it is a singleton set. When it is a singleton set, it is a singleton set when only 0 solution is there, right? So only 0 solution means it will be singleton set, right? Or it contains how many elements? Either it is singleton, or how many elements can it contain?
Yeah,
Is it?
infinitely many.
Yes, either it should be singleton or it will be infinitely many, or it will contain infinitely many elements. All right. Okay. Now, as let us have the assumption that S is an infinite set. We are not considering the singleton case. We'll consider the infinite set case. Yes. Any questions? Okay. So, if S is an infinite set, first we can observe that it is closed under addition. What is mean by closed under addition? If you take two vectors from S, then the sum of these two vectors, the addition of the vectors is also in S. How can we see that? What we know, if V1 and V2 belong to S, we know that AV1 equal to 0 and AV2 equal to 0. Right? Now, what can we say about A of V1 plus V2? This is nothing but AV1 plus AV2. Agreed? We can do this operation, right? And AV1 is 0 and AV2 is 0. So it is 0 plus 0 and hence 0.
It's also 0.
So we see that V1 plus V2 also belongs to S. Clear? Yes. So
Yes, ma'am.
V1, V2 belongs to S implies V1 plus V2 also belongs to S. So it is closed under addition. Same way, it is closed under scalar multiplication. What does that mean? So if you take any scalar alpha in R and you take a vector from S, then alpha times of V1 also belongs to S. So it means what? So if V1 belongs to S, we know that AV1 is 0. Now what about A times of alpha V1? This is nothing but alpha times of AV1, right? So here alpha is a real number. Okay. So now
0,
this is alpha times of 0. So it is again 0,
0.
right? So this means that again alpha V1 belongs to S. So this set S is closed under addition as well as closed under scalar multiplication. Okay, so do you understand what is mean by closed under addition and closed under scalar multiplication?
Yes,
No, ma'am,
ma'am.
I'm
So
not
shall,
clear on this. Can you please pardon?
which part is not clear for you?
Closed under addition and scalar multiplication.
See, it means what? We are taking some random elements from the set and we are checking whether the sum is also in the set. Also, we are seeing if you are taking a random scalar and a vector, whether the scalar multiplication also belongs to the set S. Okay, so this is what we are checking. So we see that for this set S, where S is a set of all solution of the homogeneous system, these two properties are satisfied. We will see some more examples and see whether this property is satisfied for the other sets or not. Okay, so for this set S, now we are going to see whether it is closed under vector addition or not. Okay, so how to check this? Can anyone say how to check this? How to check closed under vector addition? You first need to take two random vectors from the set, right? So let us say you have two vectors v1, v2 from S. How does v1 look like?
X1 comma 0.
Yeah, x1 comma 0 and v2 is some
X2,
x2
comma
comma
0.
0, right? Now we want to see whether it is closed under addition. So we will see what is v1 plus v2. What is v1 plus v2?
Ma'am, x1 plus x2 comma 0.
So does this again belong to S or not?
Yes, ma'am, it's wrong.
Yes. So you see that closed under vector addition. Yes. Okay. Let's see the next step. So let us take alpha in R, right? Now what is alpha V1? It is alpha.
Alpha x comma 0.
So this is also in S. So you see, this is also closed under scalar multiplication. Both these properties are satisfied, right? Okay. Now what about this set? So again, we will take two random vectors from this set, V1 in S and V2 in S. So V1 is some X1, Y1, 1
1.
and V2 is
X2, Y2, and 1.
1, right? So now what is V1 plus V2?
It's x1
X
plus
plus
x2 comma y1 plus y2
plus 2.
plus comma 2.
Okay, does this belong to S?
No.
Not, ma'am.
So this does not belong to S because you see that this coordinate here is not 1. For S, all the elements with all the vectors should have the third coordinate as 1. But this is not 1, so you have this vector. This vector is not there in S. So it means what? This set is not closed under addition. Okay. So what about scalar multiplication? So we take a real number alpha. So the scalar multiplication will give you alpha x1
alpha x, y1 and alpha.
So now, so if this alpha is not equal to 1, we can take any random real number, and for all random real numbers, this should work, right? So suppose your alpha is not 1, then what happens? Again, the same problem will happen.
Yes, ma'am. It's
This
not
does
long.
not belong to S, right? So again, the same thing. So this is not 1. Okay. So because of the same reason, both the vectors are not in S. So again, this is not closed under scalar multiplication. Okay. What about this set? What about this set? So again, we are going to take two vectors from the set S. So how do they look like? So V1 is x1, y1, where x1 plus y1 is 1.
1.
And V2 is x2, y2, where x2 plus y2 is 1.
1.
Now, what is V1 plus V2?
x1 plus
x1 plus x2 comma y1 plus y2.
What is x1 plus x2 plus y1 plus
y1. Ma'am,
1.
2? It is 2,
2
right? So, this means this vector does not belong to S.
belong to S.
Yeah. So, again, this is not closed under vector addition. What about scalar multiplication? So, alpha V1 for alpha in R. Again, here, what happens? So, you have alpha not equal to 1 we will take. So you have alpha x1, alpha y1. You will have, again, what is the sum of the vectors? Alpha times of x1 plus y1. So this is just alpha. And this is not equal to 1. Right? So again, this does not belong to S. So this is not closed under scalar multiplication. Okay.
Ma'am, why we are taking alpha not equal to 1 as a condition?
See, this condition here should be true for any alpha in R.
Right.
Okay. So now if I'm taking alpha is equal to 1, then in that case the condition will satisfy. But for alpha not equal to 1, the condition fails.
Okay.
Okay, you understand? Okay. So now look at this set. What do you think? What is your guess? Will it be closed under addition and scalar multiplication? Just tell me your guess.
Yes.
Yes, ma'am. I think so.
Okay, so if you are thinking yes or even no, just try it out and see. So this is a simple homework for you. Okay, so this one I'm leaving it as a homework. That's fine, right?
Okay.
Yes, ma'am.
Excuse
Oh.
me, ma'am.
Yes.
Ma'am, can you explain the C point again?
See, in C, the condition is that we are taking vectors such that their sum is 1, right? So the coordinates of the vectors, they sum up to 1. So we are taking two vectors such that their coordinates sum up to 1. Now what happens to V1 plus V2? The coordinates are now x1 plus x2, y1 plus y2. You know that their sum is not 1 but 2. So this sum will not belong to the set S. Same way alpha V1 is, you see that it is alpha x1, alpha y1 whose sum is equal to alpha. So whenever alpha is not equal to 1, again this alpha V1 will not belong to S. Okay, so it is not closed under addition and scalar multiplication. Clear? Okay.
Yes, ma'am.
And how the sum is equal to alpha, I did not get that.
How the sum is?
Not, I mean, how is it equal to alpha?
This one.
Yes, ma'am.
We already know x1 plus y1 is 1. So alpha into 1 is alpha.
Okay.
Ma'am, for the closed under vector addition, in this same example, the subcondition given is x1 plus y, x plus y is equal to 1, right?
Yes.
So when we are adding two vectors, x1
Hmm.
plus x2 plus
Hmm.
y1 plus y2, you are considering as 2 That part alone I'm missing. Like, can
We are not
why?
considering, we are getting it because see, we can rearrange them. If we rearrange them, so I'm just shuffling the numbers here. So when I'm shuffling the numbers, sorry. So I'm just shuffling this here and this here. That's all. Okay. Now, what is x1 plus y1?
X. Oh, sorry, one. Okay, okay, understood.
x2 plus y2.
Okay, 1, 2. Okay, understood, ma'am. Okay,
Fine.
okay, got it.
Okay. Good. Okay. So equivalently, so now we saw these two conditions, right? So equivalently means here I am saying equivalent to these two conditions together is if v1 and v2 are in S, then alpha 1 v1 plus alpha 2 v2 is also in S. Okay. So this together is equivalent to this condition. So we are combining the addition and scalar multiplication in one step here. Okay. So such an operation is called a linear combination. We will see in more detail about the linear combination soon. Okay, so this is called linear combination. So combination of vector addition and scalar multiplication. This is called linear combination of which vectors? V1 and V2. Okay. More generally, suppose we are having a set of n vectors and n scalars, then this is a linear combination of v1, v2, vn. Okay, and we know that this vector will also be in S. Okay, if this property is satisfied, then this vector will also be in S. This sum will also be in S.
Here,
Okay,
can we take alpha into V1 plus V2 like that?
so you are saying simply alpha v1 plus v2 like this
No,
or like this?
like that, yes.
Yeah,
Same scalar can be considered for both vectors.
see what is mean by a linear combination. The definition like is like this. For each vector, the coefficients are different. That is a linear combination. See, this is kind of yeah, you are literally combining these two. But usually for a linear combination, we don't do like this. Okay, so this has a deeper meaning. When we move on to the next steps, you will understand why we are taking different scalars.
Okay, so we are supposed to take individual scalars for each vector according to
Exactly.
linear combination. Okay,
Exactly.
okay, thank you.
Fine. Okay, so roughly we can think of a vector space as a collection of objects that behave similar to the vectors in the set S. What does it mean? So it means that we can perform two operations on V. What are they? We can add the elements, we can multiply scalars with the elements. So it means what? So think of vector space as a collection of objects that behave similar to the vectors in the set means, this means V should be closed under two things. What are they? First thing is that vector addition, and the second is
Scalar multiplication.
yes. Okay, so this is the first thing we are seeing. Okay, also we need some more conditions to be satisfied. Okay, so again we will see some examples before seeing what are the conditions. So I have given the first two conditions, which is vector addition and scalar multiplication. Okay, instead of just giving what is meant by vector addition and scalar multiplication, I have shown some examples to see whether a set is closed under vector addition or not. Similarly for scalar multiplication. Okay, so now we will see some examples. Can you tell me what are these vectors? What is v1 here?
1 comma 2
1 comma 2,
v2
2 comma
2
1
comma
comma
1,
1
and v3?
minus 1 comma 1.
minus
minus 1
1
comma
comma 1.
1.
Yes. So you have v1 is 1 comma 2, v2 is 2 comma 1, and v3 is minus 1 comma 1. Okay. Now what is v1 plus v2?
3, comma
3
3
comma
comma
3.
3.
And what is v2 plus v1?
3, comma
It is
3,
also
comma
3 comma 3.
3,
What is that we observe here? We see that
Commutative.
v1 plus v2 is equal to v2 plus v1. It means the addition is commutative. Commutative means what? When we shift the positions, still the value will remain the same. Okay, here addition is commutative. Okay, clear? So the next step is that,
Ma'am, the
yeah,
values can be different. I mean, if we take any other number, the values can be different.
yes. So for example, if, yeah, this confusion, I wanted to take a different point, but again I forgot. So suppose let us say your v2 is some other point, or maybe I will take some vector v. Okay, so maybe I will take something completely different. So what is this point? What is this point here?
2 comma minus 3.
Yeah.
So this is 2 comma minus 3. Okay. Now if I'm taking my v to be 2 comma minus 3, you can still see that v plus v1 is same as v1 plus v. What is v plus v1? 3 comma minus 1.
minus
Same way v1 plus v is again the same. Yeah, both are 3 comma minus 1. So this is true for any two vectors. Okay. So this is true for any two vectors. It means what? You take two vectors v1, v2 from v. This should imply v1 plus v2 is equal to v2 plus v1. Got it?
Yes,
Yeah.
ma'am. Yes.
Okay.
Yes, ma'am.
And the next thing is addition is associative. It means what? So first we will add v1 plus v2. What is v1 plus v2? We have already computed it. What is that? 3 comma 3. Now we are adding v3. What is v3? Minus 1 comma 1.
2 comma 4.
So 2 comma.
4,
We will have v1 as it is. So v1 is 1 comma 2. So we will first add v2 plus v3. What is v2 plus v3?
1 comma 2.
1, comma 2,
So you see now it is again 2
2,
comma.
comma 4.
So in either way, you see that it is associative. So v1 plus v2 plus v3 is same as v1 plus v2 plus v3. Clear? Okay.
Yes, ma'am.
Yes,
Okay.
ma'am.
So the next thing is that what is mean by additive identity. So let v be any vector in R2. Okay, any vector. Can you find a vector such that when that vector is added to v, you will still get v? What is such a vector?
Zero vector, ma'am.
The zero vector, obviously,
Yes,
right?
ma'am.
This zero vector is called the additive identity. And note that this zero belongs to your R2. That is the important thing here, right? Your zero belongs to R2. This is something very important. So this 0 belongs to R2. Now just going back here. Now for example, take this one. In this case, does 0 belong to this? Does 0 belong to S?
Ma'am, no, I think no.
No, right? So
Yes,
because
ma'am.
0 plus 0 is equal to 0,
Is not equal.
right? So it means the answer is no. It means S has no additive identity. Okay. So here we see that for R2 we have additive identity. Okay. Okay. The next step is that what is additive inverse? So the question here is that can you find a vector such that when it is added to V, you will get the sum as 0? By the way, here,
Minus V.
Yes, ma'am. Minus
minus of
V.
V.
yeah, here it is minus V. What is 0 here? 0 represents the 0 of the particular vector space. So if you are taking V from R2, then 0 means 0 comma 0. If 0 means if V is R2, then 0 means 0 comma 0. If v is R3, then what is mean by 0 here?
0, 0, 0.
Yes. So what is 0? That you should understand it from the context. Okay. So 0 should be understood from the context. All right. Okay.
Ma'am, when you say that 0 should be understood from the context, right? In the previous property, you mentioned that v plus 0 is equal to v. Is the
Yes.
same applicable that 0 comma 0 if it is an R2?
Yes. Yes. Here
Okay.
0 belongs to R2 means I am saying about 0 comma 0 only.
Okay. Thank you.
Okay. Fine. Okay. So maybe here one example let me give. So let us take some set S. S is equal to set of all x comma y such that x comma y are greater equal to 0. Now what is the additive identity in this set? Is it there or not?
Yes.
Right. First of all, is it closed under addition? Is this closed under addition?
Yes.
Yes, ma'am.
Right. So you
Yes,
can
ma'am.
note that this is closed under addition. What about closed under? Is it closed under scalar multiplication?
Yes.
Yes, ma'am.
Are you sure? What if alpha is negative?
Uh,
It should be true for all real numbers. Then only you can say closed under scalar multiplication, right? Right? So for alpha less than 0, alpha x comma y does not belong to S, right? So it is not closed under scalar multiplication. Okay. What about the vector additive identity first of all? Does additive identity belong to this set or not? What is the additive identity here? 0 comma 0
0. Yeah.
is real. That is the additive identity. What about additive inverse? If you take any vector, does it have an additive inverse?
Yes.
What is the additive inverse?
No, ma'am.
No, 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 no,
No.
no.
So for example, if you
X
take
minus
1
X.
comma 3, this belongs to S. Both are non-negative. But what is the additive inverse for this?
Yeah, it is not belongs to. So
Yes,
Minus
minus
1, minus
comma
3.
Minus 1
minus
and
3
minus 3.
does not belong to S. So this set has no additive inverse. So a set can have some property, cannot have some of the properties. Okay, so you have to verify each and every property separately. Okay. So you understand what is meant by additive inverse? Additive inverse means a vector which satisfies this property. Also, the vector should belong to the space. Otherwise, it does not make sense. A vector in the same space which satisfies the property. Okay, fine. Okay, identity of scalar multiplication. Can you find a scalar? Scalar means real number such that when it is multiplied to v, the vector is still v.
1 comma 1.
It is 1,
1.
right? So you will get back v. Okay, fine. So you have 1 into v is again v. Okay. What about
Please help with
associative?
the previous point. The one.
Sorry, any question here?
Ma'am, the previous point, v plus minus v is equal to 0. I did not understand what exactly it is referring.
So this minus v is called the additive inverse of v.
Okay.
Okay.
And
So
both
if minus,
0.
yeah, so for every v in S, if minus v exists first of all and belongs to
Yes.
S, then we say that S has additive inverse property.
So if the inverse may or may not exist, right?
Yes, it may or may not exist.
Oh,
Ma'am, in that case, we have to check for the end result of the operation, or we have to check for the whether minus v itself is existing in S.
First of all, minus v, does it really make sense or not? You
No.
have to see. Okay. And then
Okay.
only you have to see whether minus v belongs to R2 or the given set S. Okay. What is minus v? First you have to see, and then you have to see whether that belongs to S. Okay. Fine. So here associativity for scalar multiplication. We have done this for changing brackets for addition. Now we are doing this for scalar multiplication. So what is V1 if you remember? V1 is 1, 2. V1 is 1, 2 only, right? Yeah. So what is 3 times of V1? 3, 6. And now when you do twice of this, then you will get 6, 12. Now here you are first doing the scalar multiplication and then multiplying with the vector. Again you will get 6, 12. Okay. So in general, the property here is that alpha times of beta v is same as alpha beta times of v. Okay. So for all alpha comma beta in R, v in v. Okay. Fine. And here we have two distributive properties. Okay, one is with respect to vector addition, one is with respect to scalar addition. Okay, so what is V1? V1, you know, it is 1, 2, V2 is 2, 1, and the sum is 3, 3. Right? So you have 6, 6. Now, what is 2V1? 2V1 is 2, 4, and 2V2 is 4, 2. Again, the sum is 6, 6. So what is the property we have seen here? Alpha times of V1 plus V2 is equal to alpha V1 plus alpha V2. Okay, so this is for all alpha in R, V1, V2 in V. Okay, and here 2 plus 3 is 5. 5 times of V1 is, what is 5V1? 5, 10.
10.
So here you have 2, 4 plus 3, 6. So again 5, 10. So now the property here is that you have alpha plus beta v is same as alpha v plus beta v for all alpha beta in R, v in v. Okay. So here what are the things we see is summarized now. So just a recall, we first saw vector addition and scalar multiplication closed under these two things. And then we saw commutativity of addition, associativity of addition, existence of identity, additive inverse, and then identity of scalar multiplication, associativity of scalar multiplication, and then these two distributive properties. Overall 10 things we have seen. Now we are just going to summarize all the properties together. Now what is called a vector space? A vector space, yes,
Ma'am, I have a doubt.
yes,
Ma'am, 2 plus 3 into V1 is 5, 0. Then how it became 5, 10?
5, 0. It looks like 0. I am sorry for my poor handwriting. It is V1.
Oh, okay, okay. So in the below line, it is written as 10 or something else?
It's V1, yes. V1 is 1, 2, right? 5, 10.
Okay,
Got it?
got it.
Oh.
And then in the here, ma'am, 2, 4, 3, 6, how we are multiplying V1 with 2 and then V1 with 3.
Yes, V1 is 1, 2. So 2 times of V1 is 2, 4, and 3 times of V1 is 3, 6.
Okay.
Okay. So now what is a vector space?
Excuse me, ma'am.
Yes.
Before going further, can you, ma'am, please explain those line of linear independence? I didn't get that. Ma'am, linear independence.
I have not even said that word
Ma'am,
today.
ma'am, the line above, ma'am, these topics.
Yes.
Ma'am, alternative line. Ma'am, yes, ma'am. This, ma'am, these line. Yes, ma'am.
Linear
Linear
combination.
combination. Yes, ma'am. Linear
Linear
combination.
combination is a separate topic. I have covered it in detail. Just wait for it. Okay.
Okay, ma'am.
Okay. So you take a set V, okay, and you take real numbers. We say this set V as a vector space over R if first of all we need these two functions. Okay. This is the addition, vector addition, and this is the scalar multiplication. Okay. This can be defined in the way we want. Note that this means this means that we are defining. You can define in the way you want. It need not be something like coordinate wise addition or coordinate wise multiplication, nothing like that. You can define in the way you want. But the thing is that it should be closed under addition, and whatever operation you are defining, under that operation it should be closed. Okay, so we will see some examples where it is not the usual addition and scalar multiplication just after a few slides. Okay, so however you are defining this plus or dot, this dot is the scalar multiplication, you will see that that operation will be closed under this set. Okay, so for any two pair of elements in V, V1 plus V2 should be in V, and for any scalar C in R and V in V, C times of V is in V. Okay, so that is the first thing, closed under addition and scalar multiplication. Okay, next it should satisfy the following property. Okay, so now here we are having V with the defined addition, scalar multiplication with respect to real number. So what is the first one? Do you identify it already? First property, everyone just tell me the properties.
Commutative property, ma'am.
Distribute
Associative property.
associative property.
This one is
Additive identity.
exactly. This one is
Additive inverse.
Inverse.
yes. And this one identity
Scalar multiplication.
scalar multiplication. Yeah. And this is associativity for scalar multiplication. And these two are distributive properties. Okay. So set V, which is first of all closed under the addition and scalar multiplication defined, and it should also satisfy all these 8 properties. That kind of a set is called a vector space. Okay. So you see the transition slowly. First, we understood vector addition and scalar multiplication, whether a set is closed under these two properties or not. Then we saw how in R2 these properties are easily visible. Okay, and now these properties we have put together, a set satisfying all these things is called a vector space. So what is a vector space? Can you easily remember now? Yes, it is still a bunch of axioms, but it is easier for you to understand now, I hope. Okay.
So basically, ma'am, vector space, primarily we should check whether the vector addition and scalar multiplication condition satisfy, and then we need to go and check all the 8 axioms, so whether it satisfies or not.
Yes, yes,
So totally 10 in that case.
yes, yes.
Okay, thank you.
Okay, fine. So
Then what is the use of these vector spaces? Like why we are studying vector spaces? Like how it will be used?
okay, see, one very straightforward thing is that you have data set. In data set, you have this. That was the very first lecture, if you remember. We had rows and columns in a data set, and that rows and columns were represented as vectors. Row vector, column vector. That is what was supposed. Yes. So now to handle these operations, if we know where these vectors belong to, like for example, all vectors need not be R2, R3 or something, because your data set Sometimes everything need not be numericals. It can have some some address or anything can be there inside that. We don't know that, right? So to handle such things, we need some idea like vector spaces. Okay, so if we can have a vector space, certain operations are possible. If certain operations are possible, then you can actually do the calculations in some simpler way. That is the main point here.
Understood. Thanks.
Yes. Okay. To prove a set is a vector space, what is that we need to do? We need to verify additive and multiplicative closure and all the other axioms given above. Okay. And if just one of the vector space axiom fails to hold, even if one fails to hold, then V cannot be a vector space. Okay. And zero belongs to V of a vector space is always unique. There cannot be different zeros. Okay, only one zero vector is there for a vector space. It is always unique. Okay, and the real number 0 and the zero vector 0, the same symbol is used, but you should understand from the context what it means. Okay, from the context you should understand. Okay, so for example, let me see how many of you really understand what is, how to identify this. What is this 0 and what is this 0? Can you tell me?
Ma'am, zero.
Zero is a column vector.
Starting zero is a
Scalar.
scalar, and other one
And the
is
other is a vector.
vector.
Vector 0, comma 0.
Okay, so you can tell it from the context. What does it mean by 0? You can tell from the context, right? Okay, good. Very good. Okay, so usually this dot we don't write, we simply write AU or alpha U. Okay, fine. So usually the elements of vector spaces are called vectors. Okay, whatever is your vector space can have matrices also. In that case, a single matrix is called a vector. Your vector space can have functions. So a function is a vector then. So the elements of a vector are called vector spaces. Okay, so here are some examples. So Rn is a typical example of a vector space. The set of all m by n matrices. What is mean by the set of all m by n matrices? For example, if I am taking set of all 2 cross 3 m2 by 3 of R, it means set of all A11.
2 row, 3 column.
Yes. Okay, so this is a set of all m by n matrices.
Yes, ma'am.
Okay, so this is a specific case, and this was the very first example we saw today. Solutions of a homogeneous system where A is an m by n matrix. So we have m equations and n variables, right? So this is actually a vector space. Okay, you should note one thing. Where do these vector belong to? A is m by n. So X should belong to which space?
2 by 2.
Here A is m by n.
That should be n cross 1.
So it means X is a vector from Rn. Okay, X is a vector from Rn. Okay, so if X is a vector from Rn, this space is a subset of Rn, right? So the set of all X in Rn such that Ax is equal to 0 is a subset of Rn. Okay, so if a subset of a vector space satisfies, actually we'll see shortly, satisfy the first two property, closed under, maybe I'll write instead of satisfy I will say closed under addition and scalar multiplication, then the subset is called a subspace. Okay, here we know that this is a subspace. Okay, fine. Is it clear? Okay, good. Okay, so I told you the addition can be defined differently, right? So here is an example. So I have defined the addition of two vectors in R2 like this: x1 plus y1, x2 minus y2. Now you tell me, how is this commutative under addition or not? Okay, the scalar multiplication is the usual one. Addition is different. How can we check commutativity? See, here is some.
It's different, ma'am. Ma'am,
Yeah, yeah.
if we interchange them, then there is y2 minus x2.
X, yes. Okay. One thing I want to mention here, it is important, so I'm writing in red. So, to prove something, to prove an axiom, you need to prove for all vectors in the set. But to disprove an axiom, specific vectors are enough. Do you understand what this statement means?
Yes, ma'am.
Yes.
So for example, so suppose I am taking 1 comma 2 and 3 comma 5. Okay. So now what is the sum according to this definition?
Ma'am, 3 comma minus 3.
3 comma minus 3. Right?
Ma'am, 4 comma minus 3.
Yes.
Yeah,
3 plus 1
4.
and.
Sorry, yes.
1 plus 3. Sorry, 1 plus 5. Right?
1 plus 3 is 4 and then 2 minus 5 is minus 3. So now you have 3 comma 5 plus 1 comma 2, which is
4 comma 3.
4 comma 3. So you see that. So here, if I call this as V1, V2, here this is V2, V1. So you can see that V1 plus V2 is not equal to V2 plus V1. So specific example is enough to say that axiom is not holding. So you see addition. So addition is not commutative here. Okay. So addition is not commutative. Okay. Fine. Now your set is this: set of all x comma 1 such that x is in R. The addition and scalar multiplication on V is defined as follows. So now we are going to check whether it is a vector space or not. First of all, the addition is defined like this. Okay, so what is this symbol here? Does this look new? You have a colon
Fine.
and then equal to. So this means that it is defined as. Okay, so this symbol means that defined as x comma 1 plus y comma 1 is defined like this. Okay, same way c dot x comma 1 is defined like this. Now, is this vector in V or not? Is the resulting vector in V or not? X plus y comma 1, is it there in V or not? Come on.
Yes, ma'am, it should be.
Yeah, the
Because
second
x
problem
belongs to
is 1. That's all, right? So this
Yes,
belongs
ma'am.
to V. What about this one?
Ma'am, it also satisfies.
So this means that the set V is closed under addition and scalar multiplication. right? So it is
Ma'am,
closed under addition and scalar multiplication. Yes.
ma'am, in this case, addition seems to be straightforward, but if you go into the previous example, you are
Hmm.
saying x2 minus y2. That's when you say addition, then why are we redefining it as
That is
x1, x1, x2 minus y2?
here also it is not straightforward. How come 1 plus 1 is 1? We are defining it in this way.
Huh. So you
Yeah.
can always do that. You can. So you're saying addition, but actually you're not doing addition. You're
Yes.
redefining the addition to
We
a
can
different.
define we can define in the way we want. That's what I told you.
Oh, yeah,
So
yeah.
specifically, we can define in the way we want.
Okay, okay,
Okay.
okay. Right.
It is not any fixed way. We can define in the way we want.
Ma'am, in the second example, c times x comma 1, for example, if we take c equals to minus 1, then how come it become true then?
That is what I'm saying. We are defining it like this. It is
Okay,
not
okay,
equal
miss.
to. We are defining it
Okay,
that it should look like this.
okay.
Okay. Fine. Now, what is the first property?
Closed under addition.
No, that is already done. So these two are done.
Commutative, ma'am.
Commutativity of addition, right? So let's take two vectors v1, v2. So v1 is, let's say, x1 comma 1, v2 is x2 comma 1. So what is v1 plus v2 according to this addition?
X1
plus x2
plus
comma
x2 comma 1.
And what is v2 plus v1?
It is also same.
x2 plus x1.
So since x1 and x2 are real numbers, x1 plus x2 is same as x2 plus x1.
Yes.
So this means that v1 plus v2 is also same as v2 plus v1. So the first property is satisfied. What about the second one? What is the second property? What is the second property?
The associative one.
So here we need three vectors then. x1 comma 1, v2 is x2 comma 1, v3 is x3 comma 1. So what is v1 plus v2 and then plus v3? So it is x1 plus x2 comma 1 plus x3 comma 1, which is x1 plus x2 plus x3 comma 1, and v1 plus v2 plus v3 is x1 comma 1 plus x2 plus x3 comma 1. Again it is x1 plus x2 plus x3 comma 1. So both are same. So this property also holds. Right? Yes or no? Till this everything is fine for everyone? Okay? You all
Yes, ma'am.
understand? What is the third thing we need to do? This is a little different for this video. See how many of you are able to figure out. So you need to find a vector from your set V. That is the important thing here. From your set V such that you will get back x comma 1. What is that vector? If you take 0 comma
0 comma 0,
0,
ma'am.
if you take 0 comma 0, does it belong to V?
No, ma'am.
0 comma 1. No.
Okay, this does not belong to 1. Someone said 0 comma 1. Okay, let's see. So if you take 0 comma 1, what will you get? So here actually you are getting, it is x plus 0 comma 1. So x comma 1. Actually this is good. This is your additive identity. Okay. So your additive identity here, this is the 0 vector for V. Okay. So what is mean by 0 vector here? If this 0 vector is confusing, that is why I introduced the name additive identity. Let's write additive identity. Some people call it the 0 vector as well. So let's not get confused. Let's call it the additive identity for V. Okay, it need not be the origin always. It depends on how you are defining your operations. Okay, fine. So what should be the additive inverse then? what should be the additive inverse?
1, 0.
Come on, it should be a vector in V.
Minus x, comma 1.
Very good. Right? So minus x comma 1, this belongs to V, and this is the additive inverse for x comma 1 in V. Okay. So how to verify the axioms? Is this clear for everyone? So we have verified the first 4 axioms. Okay. You all understand how to verify? Yeah.
Yes.
So can you do the remaining 4 axioms? First of all, what do you think? Will it satisfy the remaining 4 axioms?
Intuitively, yes.
Intuitively, yes, right? So I recommend you all to try the remaining 4 axioms. So here, axiom 5 to 8. I'm
Will you
leaving
be
it as a,
sharing this sheet with us?
yes, as usual. Right after the session, I will be uploading it in the drive.
Ma'am, the zero vector, I don't understand that. I am little confused about.
See, what is the definition of zero vector? You should have a vector here, okay, such that when you add it, you should get back the same vector. Also, this should belong to your capital V.
Yes, ma'am.
Okay. So here, if I am taking 0 comma 1, then the sum I am getting it as x comma 1. So here I see that V plus 0 is equal to V. Or if 0 is confusing, let's say something. V plus this is equal to V. And this also belongs to, and this also belongs to my capital V.
Yes,
So
ma'am.
this is called the additive identity for V.
Ma'am, so can zero vector can be different in different vector spaces?
Yes, yes, it can be different in different vector spaces with respect to the defined way of addition and scalar multiplication. It will vary. If it is the usual addition and usual scalar multiplication, then there is no confusion. It is just going to be this origin. But when it is not the usual addition or scalar multiplication, then only you have to worry. Okay.
Okay, ma'am. Okay, ma'am.
Fine.
Thank you, ma'am.
So here I am leaving this remaining exercise as a homework. Please try it. Don't skip it. It is a very easy homework only. Please try this. Okay. Fine. Okay. So consider a set V, which is set of all x comma y's, where x and y are real numbers. With usual addition in R2 and scalar multiplication is defined in this way. So addition is the usual addition. So all the properties with respect to addition, will it get satisfied or not? What do you think if it is the usual addition?
Yes, ma'am, it would satisfy.
So that will get satisfied. Now only the scalar multiplication is very different. Okay. So now we have to see whether the properties which has scalar multiplication in it, that whether that is satisfied or not. First of all, is it closed under scalar multiplication?
Ma'am, one doubt, ma'am.
Yes.
Yes, ma'am.
I'm sorry it is out of context, but ma'am, the TA session recordings are not available either in the Google Sheet which you have shared or neither in the calendar. So
This
since
is
9 o'clock is also a mentor session, it is clashing, and I mean for 1 hour the things are not clear. I mean I'm not getting to view what all is taught.
so you are
Uh,
not getting your link for the mentor session. Is that what you are saying?
yes, TA session, ma'am, TA session.
TA session.
Yes.
TA session is not at 9 o'clock. They are on Tuesdays and Saturdays only.
So 8 from 8 o'clock TA session starts. So the recording is being done, but it is not shared. I mean, where it is shared, if someone can help or
It
maybe you
is
can
shared
help.
in the sheet, right? The
No,
Google
no, it
sheet.
is not, ma'am. It is not. I have checked. It is not shared.
But today also I asked Sanidhi. He said he has added that. Yeah, TA session recording. There is
Notes.
a drive link. Please check the calendar. In important links, So you have T is
Okay, now it has been added. Now it is added. Okay, okay. Thank you.
okay. Okay, please reserve such questions to the end of the sessions. It's kind of interrupting the flow. Okay, so this is for everyone.
I'm sorry. I'm sorry, ma'am.
Yeah. Okay. Consider the statements given below. Okay, so what do you think about the statement P?
Ma'am, it is true.
The first property is obvious, right? Because it is with respect to addition, so there should not be any problem. So this should be true. What about the second one?
Ma'am, it is also true. It is under
The
addition.
second one is again with respect to addition, so this should also be true. In fact, what is the additive identity here? What is the zero element in this case?
Ma'am, 0, 0.
0, comma
0,
0.
0 only, right? There is no change in that. So here the zero element is 0, 0. What about this one? What about this one? How can we check that? So for R, what is 1 dot V? How is it defined? So 1 dot X
1,
comma Y.
1.
How is it defined? First of all, 1
X upon
not
2,
0.
comma y.
Some definition is there. So 1 is not equal to 0. So it means the second definition. So X by 2, comma Y
Y.
1. Right? So this is just X by 2, comma Y. And this is not same as X comma Y. So 1 dot V is not same as your V. Right? So whether R is true or not,
Ma'am, it's false.
it's false. Right? Okay. What about S? S is about, so you have A times of V1 plus V2. Okay. So here, what is according to the definition, when it is 0, it becomes A is 0, it becomes 0. Okay. So here everything will become 0. So there is nothing to see. So A is 0 is straightforward case. So let us assume A is non-zero. And let us say V1 is x1 y1 and V2 is x2 y2. Okay. Now what is V1 plus V2? It is x1 plus x2 comma y1 plus y2. Now what is the scalar multiplication? The scalar multiplication is A times of x1 plus x2, right, by 2 comma y by
Y1 plus Y2 upon 2. Y upon A.
y by A, right?
Ma'am, Y1 plus Y2 upon A.
Oh yeah, sorry. Y1 plus y2 by A, right? Now what is AV1 plus AV2? So here we have A times of x1 y1 plus A times of x2 y2. Now according to the definition, this is AX1 by 2 and y1 by A plus AX2 by 2 and y2 by A. Now when we add them up, you get AX1 plus AX2 by 2, y1 by A plus y2 by A. If we simplify it further, you will get A times of x1 plus x2 by 2, y1 plus y2 by A. Right? And you see that these two terms are equal. Right?
Same.
Yeah. So your LHS is equal to RHS. So S is true or not?
It is true, ma'am.
Yeah. What about T? So your T says that A plus B times of V is equal to AV plus BV, right? So let V be x comma y. Now what is a plus bv? It should be a plus b times of x by
upon
2
2
comma y.
y upon a plus v.
Yeah. Now what is av plus bv? It is ax by 2 comma y by a
V.
plus bx by 2 comma y by b. So you get a plus b times of x. Straight away I'm writing this simplified expression, and then y by a plus y by b. What
It
about
is
the
not
second
same.
coordinates? So
Man,
you
it is
see
not
that,
same.
yeah, y by a plus b is not same as y by a plus y by b, right? So you see that LHS is not equal to RHS. So T fails.
Ma'am, in the previous case, a v1 plus v2, yeah, in that a into x1 plus x2, y1 plus y2. The right side RHS you have taken because this is greater than 0, right?
Where?
A x1 x2 by 2,
Hmm.
that we have taken because in the for equation piece function it has given that x1 x2 is greater than, it will always will be greater than 0, right?
It has nothing to do with greater than 0 or anything. We don't have any such conditions.
No, c of xy is given, right, above the
Yes.
question. Yeah, cx by 2 comma y by c. So
Yeah.
c is not equal to 0, then only we will take it as am I confused?
I guess instead of this condition, you assume some xy positive. So only c not equal to 0 is there. So for that correspondingly, I have taken a not equal to 0. Okay.
Okay, 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 good.
Okay. So is this question clear for everyone? Yeah.
Yes, ma'am.
Okay. Good. Okay, so we have the usual, see, when we are doing the usual addition, we have the cancellation properties, right? Right. So the same cancellation property works here as well. It means what? If you have v1 plus v3 equal to v2 plus v3, then v1 should be equal to v2. So for any vector space, the cancellation law of vector addition is there. So you can cancel out these terms here. Okay. And as I already mentioned, the additive identity, the 0 means the additive identity here. Additive identity is unique. Okay. And the additive inverse, okay, is unique. So usually it is referred as minus v. Okay. Fine. Okay. So next we are moving to what are subspaces. Already I have given the definition. So let us recall it again. So let us take first of all a non-empty subset, okay, of vector space V. We call it a subspace if V is closed under addition and scalar multiplication. Okay. So here the same operations you should use. So for example, so you see that, yeah. So this we saw, not this one. Yeah, this one we saw that here the operations are different. So if you want to consider a subspace, then for that set also you should consider the same operation. You cannot consider some different operation. Okay, that is what here they are saying. So we should consider under the operations addition and scalar multiplication defined in V. So you cannot take different operation for the V and W. The same kind of operations only should be there for W and V. Okay. So for a subspace, you don't have to check all the axioms of a vector space. It is very easy. You can simply check closed under addition and closed under scalar multiplication. That is enough to check the conditions of a subspace. So only these two conditions are enough. Then you can say that W is a subspace of V. Okay. So we will see some examples here. So for every vector space, what are the trivial spaces? The whole vector space and the zero vector. These two are always subspaces for any given vector space, right? Because you can obviously see they are closed under addition and scalar multiplication, right? So what does this symbol means? The zero vector in V. Okay, the zero vector in V. Okay, so what is the zero vector? I already told you, this is the additive identity I am talking. Okay,
Ma'am, what in some cases additive identity is not defined, then
then it cannot be a vector space itself.
okay, okay, okay.
Okay, fine. So check whether W set of all x plus y is a vector space, vector subspace of V equal to R2 or not. Okay, so how to check whether it is a subspace? What are the two conditions?
Closed under addition and scalar multiplication.
Yeah, so you take two vectors V1, V2 in W. V1 equal to x1, y1 and V2 equal to x2, y2. So what is V1? What is the condition? First of all, we have if they are in W. If they are in W, we know that x1 plus y1 is 0. Same way, x2 plus y2 is 0. So now what is V1 plus V2 here?
X1 plus
Plus
X2
x2.
Y1 plus Y2.
Now what is x1 plus x2 plus y1 plus y2?
It
Again,
is 0.
yeah, you just have to simply rearrange the terms to see it. Already know that these two are 0, so you will get again 0, right? So you see that V1 plus V2 belong to W. What is the next condition? You take V, which is xy, and you take alpha in R, and now you know that this V, if it is in W, then x plus y is 0. So what will you have? Alpha times of V is alpha x comma alpha y. So alpha x plus alpha y is alpha times of x plus y. So it is 0. Okay, fine.
Okay, ma'am.
So you see, again, alpha v belongs to W. So W is a subspace of R2. Okay. So geometrically, what does this W represent? It represents a straight line in R2. What is specific about this straight line?
Passing through the origin.
Yes, it passes through the origin. This line L, so if this is L, so L passes through origin.
Then the set of all vectors for which x plus y equals to 0 becomes a subspace of
Yes,
becomes a subspace for
yes, that is what we just proved here. Yeah, so that becomes a subspace of R2, right? So from the above graph, it is clear that L passes through the origin. In general, a line in R2 is a subspace of R2 if and only if it passes through the origin. So for example, so what do you know about line passing through origin? So first, what is the equation of a line in general? Y equal to,
Mx plus
MX
c.
plus C.
right? If C is equal to 0, then
Y equal to MX.
the line passes through,
Origin.
Origin.
right? And if C is non-zero, then the line does not pass through origin. Right? So you see that, so whenever the same thing, right? So if you take W is equal to set of all x comma y such that you have this mx y is equal to mx condition. Here what is the condition? Y is equal to minus x. This is equivalent to what? Y is equal to minus x. Here your m is equal to minus 1, right? So instead of that, here you are having y is equal to mx. Okay. So if you are having something like this, or equivalently, you can have ax plus by is equal to 0. Either of this form. Just the format is different. Okay. So then you know that the line passes through the origin and it is a subspace of R2. You can easily verify these properties will hold. Okay. And if it is not passing through origin, then what will happen? For example, just consider, for example, this line x plus y is equal to 1. Does it pass through origin?
No, ma'am.
So,
And it is not a subspace also.
yeah, trying to draw a line here. Yes, somewhat looking like a line. So you see, this is not passing through origin and it is not a subspace. What happens when a line does not pass through origin? The zero vector will not be there, right? So you see, for these lines, 0, comma 0 will not be in L in this case, right? If 0, comma 0 is not there, then additive identity is not there. If additive identity is not there, you can say it is not a subspace. So this is a shortcut to verify whether a set is subspace or not. You can easily check whether the zero vector of that space is there or not. From that, you can say. Okay. So this is a shortcut. I guess I have mentioned it somewhere.
One clarification needed.
Yes, yes.
Um, a zero vector is not always 0, comma 0, right?
Yes, but here we are talking specifically, we are talking about subspaces of R2 under usual addition and scalar multiplication.
So in that case, like in a plane, in a R2 plane,
Mm.
0, comma 0 is always expected to be the zero vector.
Yes, that is what I told you in the beginning also. Maybe for more clarity, I will specifically write. So in Rn, with usual addition and scalar multiplication.
Okay, with usual, not like the defined one. Okay,
Yes.
okay, understood.
Origin is the additive identity.
Okay, thanks, man. Now it makes sense. Thank you.
Yeah. Okay. So,
Excuse me, ma'am.
yes.
Ma'am, you say that there is no additive identity. That's why this is not a subspace.
Mm.
But ma'am, for subspace there is only two condition. No? The addition one and the scalar multiplication one.
Yes.
So ma'am, how additive inverse?
So
I
if
didn't get that.
Yeah, let me answer your question. So if 0 does not belong to V, I am saying that W is not a subspace, right? But what I actually defined as a subspace, I just wanted that these two conditions should be satisfied, that it should satisfy closed under addition and closed under scalar multiplication. Now I am saying only this is sufficient to say something is not a subspace, right? I'm see very clear that be very clear that I'm using this condition only to say it is not a subspace. So I'm not using this to prove something is a subspace. I'm using this only to disprove something is not a subspace. Okay, that distinction you should have. So let me explain that. So if 0 does not belong to W, what will happen? If 0 does not belong to W, then both this condition will fail. How? So if 0 does not belong to V, the first one, so if you take V in W, you take any V in W, okay, so V plus minus V should be 0, right? Yes or no?
Yes, ma'am.
So that if, but you see that if it is equal to 0, then it should belong to W. But already this is not there in W. Yeah, I'm taking these two vectors v and minus w from w.
Okay, ma'am. Okay, got it.
Yeah, then you see this property fails. Okay, and also now if I am taking 0 in R and 0 times of v, I know it is 0, but this does not belong to w. So you see that both this property will fail. It's
Okay, okay,
totally
ma'am.
Since 0 is a trivial subspace for R2, so that's why it's failing.
no, that is something different. 0 is a trivial subspace, so that is when only 0 is there. So now here I am saying when W has so many things apart from 0, we should make sure that 0 is also there. 0 should always be inside W. That is what I am saying here. Okay, so this is a shortcut to check whether something is not a subspace. Okay,
Okay,
fine.
ma'am. So if we want to prove something, that we should check the two properties, and if we have to disprove the subspace, then we can use the other properties, eight properties of the vector space. If uh,
See, usually we don't go back to the 8 properties for a subspace. For a subspace, we have very simple conditions, so we don't go back there. Okay.
ma'am, earlier you disproved the additive identity. Yes, ma'am. Here. So yes, ma'am. Here.
I am saying this condition fails. The condition of the subspaces. These two are failing. Okay. I did not go back to any axioms. I just said these two are failing. Okay.
Yes, ma'am. Got it.
Okay. So it is possible that 0 vector is there in your W, but still it is not a subspace. That is also possible. For example, look at this. Here you see that 0 comma 0 belongs to W, right? But you are having a parabola. Will it be closed under addition?
No, ma'am.
Right?
Example is 1 comma 1 and 1 comma
Yeah,
minus
you take these 2 points. What are these 2 points? 1 comma 1
Minus one.
minus 1 comma 1. What is the sum of these two vectors?
0 comma 2.
0,
0 comma 2. So somewhere here, right? So somewhere, sorry, 0 comma 2. So this point, sorry. So you have 0 comma 2. So you obviously see that 0 comma 2 is not there in W, right? So if you take V1 is this and V2 is this, then V1 plus V2 is this, and it is not there in W, right? So W is not a subspace. Is that clear?
Yes, ma'am.
Yeah. See, do you all remember how I explained the scalar multiplication in R2? Yeah, so it should just, whatever scalar multiplication you do, it will just simply lie on a straight line in R2. Yeah,
Yes.
yes. So from that, you can easily see that scalar multiplication property will obviously fail because it is a curve. And when you do scalar multiplication, all the vectors are going to lie on a line, right? So from that also you can say scalar multiplication, this is not closed under scalar multiplication. Okay. Okay, so here something different we are going to consider. So please concentrate. So we have seen so far examples from Rn and subsets of Rn. Now we are going to look at matrix spaces. So it is very similar to the concept we saw in Rn, just that now we are having matrices. Okay, so let's say you have a subspace set W where you are having set of all 2 by 2 matrices such that A is equal to A transpose. It means what? We are considering the set of all 2 cross 2 real symmetric matrices. Okay. So whether this is a subspace or not with standard addition and scalar multiplication. Okay. So first of all, what is W? We have to break down. Okay. So it is given that it is 2 by 2. So first of all, 2 by 2 means the structure is usually, we write it like this. The next thing is A transpose is equal to A. It is symmetric. So if it is symmetric, what do you know? Aij is equal to Aji.
AGI.
So which elements are equal?
C and B are equal.
So you have A is equal to A, B, B, D. Okay. So A belongs to W means A belongs to W implies A is of this form. Okay, A is of this form now. Okay, if A is of this form, now we have to take two vectors. So let's say V1 is A1, B1, C1, D1. Okay, this is in W. And V2 is A2, B2, C2, D2. Now what is V1 plus V2? A1 plus A2, B1 plus B2. Here, hold on. I wrote it as C1 itself. So let's write it as B1, B2, D1, D2. Right? So if I'm giving, so for easier understanding as matrices, let me rename them as, sorry, A1, A2, A1 plus A2. Right? Now you can clearly see that A1 plus A2 whole transpose is same as A1 plus A2. So this means that A1 plus A2 belongs to W. What about alpha A1 or alpha A? So alpha A, so A belongs to W. Now alpha A is simply alpha A, alpha B, alpha B, alpha D. So this is also very straightforward. Alpha A whole transpose is same as alpha A, and hence alpha A belongs to W. So it means what? W is a subspace. Subspace of M2 by 2 of R. Okay. So in the case of matrices also, the process is exactly the same. Is this example clear for everyone?
Yes, ma'am.
Yeah?
Yes, ma'am.
Okay, good. So the next condition is, next set is set of all W where you have 2 by 2 invertible matrices. Whether this set is a subspace or not. Set of all 2 cross 2 matrices such that it is invertible. What is the condition for invertibility of a 2 cross 2 matrix?
Determinant A is
Determinant
not
not
equal
equal to 0.
So what is the determinant?
to A D minus
A
BC
minus
should not be equal to BC.
Okay. So now I have a question for everyone. Let me see how many of you can quickly answer this question. If if I'm saying you should prove that it is a subspace or not, but you should not use closed under addition or closed under scalar multiplication, then which property will you use?
additive zero vector, whether the zero vector is
Additive
within the
identity.
Yeah. So what is additive identity? The zero
It
matrix.
gives
zero.
the diagonal matrix.
So this
Sorry,
is
null
the
matrix.
additive identity of
Phase.
M2 by 2 of R. Right? And is this there in W?
No.
Okay, because this is not invertible, right?
Yes.
So this is not in W. So you can say that W is not a subspace. Right? Is this clear?
Yes.
Yes.
Yes, ma'am.
Fine. Okay. So here one thing I wanted to mention. I guess I mentioned it somewhere here. Yeah. So what did we see for R2? For R2, what are all the possible subspaces? Either it can be just the origin alone, or it is any line which passes through the origin, or it is the entire plane. These are the only subspaces of R2. Okay, there cannot be any other space subspaces apart from this. Okay, for R2. Now we are moving to R3. Okay, so in R3, what does this set represent first of all?
X2,
Ma'am,
X3.
YZ plane.
This is the YZ plane in R3, right? This is the YZ plane in R3. So now it is very easy to check. So let us take two vectors v1, v2 in W. So v1 is 0, y1, z1. v2 is 0, y2, z2. Very easily v1 plus v2 is 0, y1 plus y2, z1 plus z2. So obviously in W. Same way, alpha times of V is 0, alpha Y, alpha Z in W. So you see that W is a subspace. Right? Subspace of R3. Now what about this one? What about this set? This is a plane. Right? Just like we saw equation of line. So here you see that AX plus BY plus CZ equal to 0. Okay. So AX plus BY equal to, okay, maybe I will write D. So this is a general equation of a plane in R3. So if D equal to 0, so it is a plane through origin. And if D is non-zero, it is a plane not containing origin. So now I have already given the answer to you. Can this
Yes,
be a
ma'am.
subspace?
No.
No.
Because X plus B
No,
plus
ma'am.
C does not equal to 0.
So W is not a subspace of R3. Okay, so what about this one?
Not yet.
So you are having X greater equal to Z.
Z.
Is this a subspace or not? What is your guess?
No, because this like fails scalar
Yeah,
multiplication.
scalar multiplication will fail, you are saying.
Yes.
Okay, so let us take some vector where this property is satisfying. Let us maybe take X is maybe 2 and this is 1, 1. So this is a vector in W, right? Now what happens when I multiply with minus 1? It becomes minus 2, minus 1, minus 1.
X
Now
become
this
lesser
is that
than Z.
yeah. So you see that the X coordinate is less than Z, right? So this means that this does not belong to W. So W is not a subspace. Clear?
Even if we find a single example, we can claim that it is not.
Exactly, exactly. That's what I actually wrote somewhere. I don't know where I wrote, but I wrote, yeah. To
Yeah,
prove
it is.
something, you need to prove for all vectors. To disprove, specific vectors are enough.
Okay.
Okay? Fine. Yeah. So we saw what are all the possible subspaces of R2. Same way for R3, it should be either the zero space or they are lines through origin or they are planes through origin and or it is the entire R3. So these are the only possible subspaces of R3. There cannot be anything apart from this. These are the only structures in R3. See, what is this? Under which topic of mathematics do these topics fall? The topics we are studying,
Linear vector spaces. Okay.
linear algebra, right?
Yeah.
Yeah. So the topic is about linear structures. So from there itself, you can have a feeling why these are the only subspaces. See, linear means you can understand, right? Something like a line or a plane without any curves. That is what is linear structure, right? So you can see that the subspaces here are the linear structures inside the set. It is either a line or it is the plane. Okay, so these are the linear structures. Okay, so just to give a feeling of why, see, yeah, of course, why you can see from the definition, but just apart from the definition, also some meaning is there. Just wanted you to have a feeling of that. Yeah.
Why it has to be only a zero subspace or the entire subspace? Why not in between? What is there a reason behind that? Why we don't consider uh, non-zero subspace as a non-zero space as a subspace? The
Apart from
lines.
lines or
uh,
planes, you are asking?
yeah.
That is what I actually told you just now. See, apart from lines, it should be some other curve, right? If it is not line, then it should be some curve.
No,
But
ma'am.
what?
Yeah, that part I understood. But for example, if the line is passing through the origin, then we are saying zero space, zero subspace, right?
No, no,
Or
no.
we are
No. It is a subspace only. I'm saying zero subspace is different. Zero
oh,
subspace means only the zero vector.
zero vector.
This is the zero subspace.
Okay.
This is the zero subspace in R3.
Okay.
Okay, so these are something different.
Yeah.
It's a
Zero.
point, right?
Yeah, it is just one single point here. So it is
Yeah.
entire line. It is entire plane.
Correct. But either we are saying line through origin or plane through origin or entire space. So
Yes.
we are eliminating all those lines which are not okay. We are not eliminating actually. Anything non-passing through the origin is falling under entire space. That's what we are saying.
Not falling under entire space. It is not a subspace. That's all.
Hmm.
Anything which is not passing through origin, what happens? For example, here it
Hmm.
is not containing the origin, so the criteria for a subspace is not satisfied by that set. That's all. For example, this one is a line, but it is not a subspace.
Ma'am, can union of two subspaces be a subspace?
You tell me. You take this, all the vectors here, all the vectors here. Can they? Okay, two subspaces you are saying. Okay, so let us say you are taking this and this. Okay, do you think the union is a subspace? So for example, so set of all y is equal to x and y is equal to minus x. So this is your w1, this is your w2. Okay, so 1 comma 1 belongs to w1 and 1 comma minus 1 belongs to w2. Now both of them belong to w1 union w2. Yes, so they belong to w1 union w2 as well, right? So now what happens to their sum? 1 comma 1 plus 1 comma minus 1. It is 2 comma 0. Does this belong to w1 union w2?
No, ma'am.
See, whenever you have a question, I recommend you, yeah, you are asking me, first of all, participating in the class, I appreciate it. But I recommend you give it a try to answer your own question. Okay, it's good to come.
Actually,
Yeah.
I was in self-doubt that's why I asked.
Okay, fine. That's good. If you have tried and then asking, that's very good. Okay, good. Okay, so shall we move to the next example? Everything clear so far? Okay, good. Okay, so now some more examples in the case of matrices. So first example we already saw. What was the answer? This is a subspace.
Subspace.
What about this one? What is V2 first of all? How does V2 look like? V2 looks like this, right? They are set of all scalar 2 by 2 scalar matrices. So it is set of all alpha, alpha, 0, 0. Alpha in R. So do you think this is a subspace?
Yes, ma'am, it is.
Obviously, this is a subspace, right? What about V3? V3 is set of all diagonal matrices.
Yes, ma'am, it is.
So again, this is also
Subspace.
subspace.
Space.
What about V4? Upper triangular matrices.
This is also a subspace.
Alpha, beta, gamma. Again a subspace. What about V5? Lower triangular.
It is also.
This is also.
All are subspaces.
This is also, it's getting shorter and shorter. I'm going to write just S then. Subspace. So all are subspaces of M2 by 2 of R. Okay. So this example is a very easy one, right? Yeah.
Yes, ma'am.
Yes, ma'am. Can I add an example? Like,
Sorry, what?
can I suggest an example?
Yes.
Set of all polynomials degree less than 2 with real coefficients.
Yes, yes, you are saying a good example only, but this is not the place where I can explain this to the other students because we are not considering polynomial for this course. Yeah, but your example is valid.
Okay, ma'am.
Yeah, good. Okay, so the next interesting topic we are here. So some people were asking about linear combination. So here is the topic. This is something very important to understand. So everyone concentrate here. This is a very simple topic only, not something very complicated, but very important. Simple but important. Okay. So we are having a vector space V and we are having a set of vectors from V. What is mean by linear combination? A linear combination of the vectors v1, v2 with coefficients a1, a2, an is the vector this. So it means what? a1, v1 plus a2, v2 plus etc. an, vn. So this is called a linear combination of v1, v2, vn with these coefficients. Okay. So generally a vector v in V is a linear combination of some vectors if we can write V as AV1 plus A2V2 plus ANVN for some scalars. Okay, for some scalars. Okay, so it means what? Suppose I am having, let us say 1, 2. Can I write it as a linear combination of these two vectors? What is your answer? Can I find some coefficient which satisfies this equation? Any suggestions here? What should be my A1? What should be my A2?
So A1
A1
should be
is
1
1
and A2
and
is 2.
A2 is
A2 is
2.
2.
Yeah. Okay. What is mean by linear combination when I have only one vector? So when I have only one vector, linear combination means,
Anything multiplied by v1 will be a linear combination.
yeah, so
Scalar.
just scalar multiples. Right? Linear combination of V1 is simply scalar multiples of V1. Okay. Fine. For one vector, it is just scalar multiples. For several vectors, so it is of this form. Okay. So
Ma'am,
here,
this A1 can be 0 also. You mean then
yes,
it
it
will
can
become
be
a
zero also. Yes,
zero
it,
magnitude. Zero magnitude. Okay.
yeah, yeah. It is possible that it is zero, right? For example, suppose I am having 1, 2 is equal to, so let us say it is some 3, minus 1 and 1, 2. So what can be the coefficients now? Here,
1.
this is 1
From 0, 0
and this
and
is
1.
1.
0, 1.
Okay. Another question, let me ask the same 1, 2.
We can do 0 and
One
1
and
here also.
0, 1 is one possibility. Are there any other
And
possibilities?
another, yes, ma'am,
one and two.
1 upon 2 and 0.
Okay, 1 upon 2 and 0. This is another possibility. Any other possibility? Someone, this is something very simple. Someone should try.
-1
-1?
and A2 would be 2.
Oh, okay. Something straightforward, I thought. So here it is 1 and here it is -1. Yeah, this will also work, right?
That is also.
Yeah. So many possibilities are there in this case. Why is that so? Okay, this is something you should think. Okay, so we will come back to this after completing linear combination. Keep this in mind. Okay, this is some interesting thing we have done here. We will come back to this. Okay, fine. So let us first try to understand visually what is going on. Okay, we already know what does scalar multiplication do, what does addition do. Now we are combining both. So what is happening? We are seeing. So what is this vector here? This blue vector, blue dot. What is that vector?
X1 vector.
This is
Axon vector.
-1. This is 1. So what is that vector?
One,
-1 comma
sorry,
1.
-1 comma.
And this is
2 comma 1.
2 comma 1. Okay. So x1 is -1 comma 1 and x2 is 2 comma 1. Okay. So now C2 x2 is something like this and C1 x1 is something like this. So specifically when C1 is 2, you get 2 times of x1, which is -2 comma 2. And when C2 is equal to 3, you are getting,
6 comma 1.
yeah. So you are getting 6 comma 3.
6 comma
Okay.
3.
6 comma 3 is what you have got. Now, you know that if these are the two vectors, then the sum of these two vectors is this parallelogram, diagonal of this parallelogram, C1x1 plus C2x2. So nothing new is happening. Whatever we already know, we are doing, performing those operations, and then we are getting the linear combination. We first did the scalar multiplications and then we added them up. That's all. Okay, nothing new is done here. All right. So this is the simple visualization. So here you have C1x1 plus C2x2 is equal to, this is the point 4 comma 5. So this is 4 comma 5. So this is 6 comma 3. This is your 3. And here this is -2 comma 2. This vector is, 6 comma 3. I wrote. So you can compute and see exactly what is going on here. Right? 2 times of -1, 1 plus 3 times of 2 comma 1. So -2 plus 6, 4, 2 plus 5, sorry, 2 plus 3, 5. Right? So what is the linear combination? Is that clear? This combination of scalar multiplication and vector addition. Yeah. So let v1 equal to 1, 0 and 0, 1. I have already asked a question here. Anyway, so can you write this vector as a linear combination of v1 and v2?
Yes, ma'am.
Yes, ma'am.
So what are the coefficients?
5 and -1, -7.
So in general, if you have any vector x comma y, what are the coefficients?
X and Y.
X and y. Okay. So these are the notations. Sometimes it is more generally referred to as E1 and E2. And this is called the standard
Standard basis.
basis of R2.
Yes.
What is the basis we will see? Just I'm saying, because we are introducing it for the first time this set, the name of this set is standard basis of R2. Okay, we will see about what is the basis and all maybe in the next session. Okay.
Somewhere else you referred this term as unit vectors, right?
Yeah, they are unit vectors as well. Yeah, they are at unit distance from the origin. Yeah,
Okay.
right. Okay. So can you express V as a linear combination of V1 and V2? Is this possible? Yes. How to see that? So can we write 5 comma 6 as a1 times 1 comma 2 plus a2 times of 1 comma 1. So rewriting this, you get 5 comma 6 is equal to a1 plus a2 comma 2a1 plus a2. So when we equate the components, we get a system of linear equations. Can you quickly solve this system and see whether it has a solution or not?
So A1 equal to 1 and A2 equal to 4.
A1 equal to 1 and A2 equal to 4. So A1, this first one is fine. 2 A1 A2, yeah, it's fine, right? So you can see that A1 and A2 are solutions for this, right? Okay. What about this? Again, I leave it as an exercise. You all complete it and tell me the values of A1 and A2. First of all, do they exist? If they exist, what is the answer?
Okay, ma'am.
Yeah. Did anyone solve it?
Attempting. Give us one more minute.
Sorry?
Just trying to solve.
Yeah, yeah, yeah.
Minus 5 and minus 8.
Okay, so minus 5 times minus 5, and then here 8 twos are 16. Why? No, 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 not the answer. A1 is
Minus 7 and minus 5.
yes.
Minus 7 and minus 5.
Minus 5 and 7.
Yes, minus.
Minus 7 plus 10 is 3, yes, and then 7 minus 5, 2. Good. This is good. Okay. So you know how to write a given vector as a linear combination of some other vectors or not. Okay. So if v equal to v1, v2 are vectors such that v equal to a1, v1 plus a2, v2, then each of the vector is a linear combination of the other two vectors. Do you agree? Yeah.
Yes.
So you can write here v1 as, maybe you have to divide everything by a1. So maybe I have to write 1 by a1 times of 3 by 2 minus a2 by a1 times of v2. Or you can write v2 as 1 by a2 times of v minus a1 by a2 times of v1. So you can write each of the vector as a linear combination of the other two vectors. Right? Okay. So 0 vector can be written as a linear combination of v, v1 and v2. Right? So if V is equal to A1V1 plus A2V2, then what does it say? V minus A1V1 minus A2V2 equal to 0. So it means what? 0 is a linear combination of V1 and V2. Yes or no? Yeah.
Yes.
So what is the other possibility? So one, here I am having non-zero coefficients. So when I am writing like this, the coefficients are 1 minus A1 minus A2 are the coefficients. But it is also possible that I can write them simply with 0 coefficients. Both are possible, right? Both this scenario is possible in this case. Okay, but it is not always possible that both 0 coefficient and non-zero coefficient will exist. Okay, so if you are writing some vectors as a 0 as a linear combination of some vectors, then it has some specific significance. Okay, we will see it. Okay, so now this is the standard basis of R3. Why? Because you see any x comma y comma z can be written as x times
X
of,
times V1
yeah,
plus Y times of V2 and Z times of V3.
yes. Okay, now can you see whether V is a linear combination of V1 and V2? 372, is it a linear combination of V1 and V2? So you have 2 beta is equal to 3 and 2 alpha plus 2 beta equal to 7 and alpha equal to 2. So it means you have alpha equal to 2, beta equal
Beta is 3
to
by 2.
2. Will it satisfy this equation? We have to check. 2 times of 2 plus 2 times of 3 by 2 is 4 plus 3, 7.
Yes, satisfied.
So this is a solution. Okay. So the plane containing these 2 points is given by this. So how we have got this is not required for now. Okay. Even for the whole course, it's not required. So just let's consider the plane containing these 2 points. Okay. So why these 2 points are in this plane? Because you see that V1 is 0, comma 2, comma 1. And you see that 2 times of 0 minus 2 times of 2 plus 4 times of 1 is 0. Same way V2 is 2 comma 2 comma 0. So 2 times of 2 minus 2 times of 2 plus 4 times of 0 is again 0. So V1 and V2 belong to this plane, right? So V1 and V2 belong to this plane. Now let V be any linear combination, not necessarily this V. V is any linear combination of the vectors V1, V2. Does V lie in the plane containing V1, V2? What is your answer?
Yes.
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 Yes. This is because your plane is a subspace
Yes.
of R3, right? And it is closed under addition and scalar multiplication. So closed under addition and scalar multiplication. Let me just keep it short. Okay, so this together and together gives linear combination. Closed under linear combination. Okay, so if you are verifying both these two or just linear combination, everything is same. Okay, fine. So here we see that since subspaces are closed under addition and scalar multiplication, they should also be closed under linear combination, because linear combination is simply combination of these two operations. So is this question clear? Why the answer is yes? Is it clear for everyone?
Yes, ma'am.
Good. Let W equal to 1, 2, 0. Does this vector belong to this plane? Just
Yes.
check. 2 times of 1 minus 2 times of 2 plus 4 times of 0. What is that? 2
No,
minus
ma'am.
4.
No.
No.
So it means W does not belong to the plane. So if W does not belong to the plane, can W be written as a linear combination of V1 and V2?
No, ma'am.
No. So if W is there in a plane, then we should be able to write this V1 and V2 as a linear combination. You can check this. Okay, why we cannot have this? That we have not yet covered, but we cannot write. You can verify this. Okay.
Ma'am, if you can go back to that same question, where so W is a vector 1, 2, which is defined as 1, 2, 0, right? That 1, 2, 0, I can still define it like a linear combination, right? It need not to be part of any vector, right?
Okay. So I'm asking specifically here, what is the V1? 0 to 1.
Okay. It
V2
is
is 2 to 0, right? Yeah.
okay, understood.
So specifically, if we are taking this, my 1, 2, 0, can it be?
Represented as okay. Okay, understood. It
Okay.
cannot be. Now I understand.
Why it cannot be? Because 2 beta is equal to 1 and 2 alpha plus 2 beta is equal to 2 and alpha is equal to 0. So if alpha equal to 0 and beta is equal to 1 by 2, this equation is not satisfied, right?
Hmm. Yeah.
So this has no solution.
Yeah.
So this means W cannot be written as a linear combination of V1 and V2,
Okay.
right? That without even verifying, we can say it that W, since W is not in the plane, we can say that it cannot be written as a linear combination of V1 and V2. That we will understand how slowly. Okay, for this point, you can just note that if W is not in the plane, then it cannot be written as a linear combination of these two vectors. Okay, fine. Can we write 0 as a linear combination of the vectors V1, V2 and W? A quick answer from someone. Can we write 0
Can
as
be.
Yeah, we can, right? If
Yes.
the scalar is zero,
yes,
generally it becomes.
yes, very good. So obviously this is one answer. This is one answer. Good. So now what about non-zero scalars? Non-zero coefficients, is it possible? Is it possible to have non-zero coefficients?
It is possible if we take
If it's a base.
some negative scalar.
So I will stop today's session with this question. Try to find non-zero coefficients. Okay. So I'm
Okay, ma'am.
stopping. So everyone try this one and we will continue with the same question in the next session. Yes, any questions? Okay, so
Question,
yes.
the question is that can we write non-zero scalars as equal to zero, like non-zero?
So my question is, can we find non-zero scalars alpha, beta, gamma such that alpha v1 plus beta v2 plus gamma w equal to 0?
No, ma'am.
Yes. Huh? What? No.
No.
How can you say no?
Because only V1 and V2 can be represented as a linear combination,
and W is already we have found that it is not it doesn't come under the linear combination of these vectors.
Yes, that is why your answer is wrong. The justification you said exactly. The justification is correct. W cannot be written as a linear combination of V1 and V2. So your answer is wrong. Think about this again. Okay, think about this again.
Okay.
Try to verify it step by step. You will find the answer.
Yes.
Okay,
Yes.
okay. Please try it. Good. Okay, so any other questions? Okay, so I just want to know the general feedback regarding the sessions. How is the session going? So, do you find my sessions smooth? Is it fast,